Alright, a video on a couple of subjects, I think, hopefully. Energy related, kind of. Photoelectric effect. And then the subject of E equals mc squared and the calculations of the energy produced by atomic chain reactions and such. So we'll start there. I don't know if these subjects are that related, but they seem to me to be somewhat related in understanding what exactly is stated when stuff is stated. So there's this thing called atomic weight, and then there's atomic number, and then there's mass. And I always thought they were somehow the same thing, but apparently the atomic weight is just the stuff inside the atom, protons and electrons and neutrons, and adding them up. And the other weight, mass, is something else, because the mass is always more than the weight, technically. And in a nuclear reaction, you get the same atomic weight back, but you don't get the same atomic mass back. So there's a release of the extra energy. And somehow this applies to E equals mc squared, but it obviously would apply in the sense that the equation isn't really saying mass is energy in the sense of weight is energy. It's saying that mass has a component that makes energy, makes weight significant. So the weight itself doesn't have the energy, it's the mass element, another mass element, that isn't considered a atomic element, is where the extra mass that would be associated with the energy. So basically just saying there's something between the bits, and that something has a mass, technically they're saying, that somehow, I don't know if it's actually measured, that is different than the atomic weight by itself. So big things have more mass than atomic weight. Yeah, something like that. As you bring things together that have atomic weight, their mass increases. It's probably a simple way to say it.
2 barium and krypton and 3 neutrons, and in the process releases the binding energy. And they claim that the energy heats the water. That's never explained. I looked all over the internet. No one explains how energy, as a general concept of energy, even binding energy specifically, how it heats water. No.
So I think that is, well, I mean, it might not be explained because it's kind of obvious that the energy would be in the form of radiation, in the form of gamma, little bits of stuff, photons, and maybe a ton of them in the infrared range, and certainly ultraviolet and gamma and X-rays are all released through this process. So there would be lots of little ray bits that are the binding energy.
Explanation. But they get the energy using the calculation.
I would argue more specifically from my point of view, you could almost call it gravity. So a nuclear bomb is also releasing gravity bits.
E equals mc squared. Okay, well, in the particle model, I've talked about this before, nuclear binding force. The particle model explains the binding force of the nucleus and the atom using G2 gravity. That's our explanation.
Right, and the problem with that explanation is that we sort of already know that you can't do that. I mean, that the Mach gravity kind of thing, the particle gravity, can't do the big thing right and then do the small thing. It doesn't have enough energy to do the small bits. They're moving too fast to have too little mass, so they don't work like solar systems. So you can't use the gravitational model to explain atoms. There has to be something else. You have to understand that somehow the force is magnified, like magnetism.
The G2 binding force is not part of the nucleus or atom. The G2
So again, I would say that you can sort of understand on its face that probably isn't right, just because gravity is the only force we know of, to explain a lot of energy that exists in things. So the molten core of the Earth the only rational way to explain that is to explain that gravity is causing it, because gravity is pulling two different directions, pushing in different directions, creating pressure in different directions, and creating a lot of heat through that tension, through that shear, through that torque. So there is energy trapped inside of the Earth from gravity. And so you already have a door open to the idea that energy can be trapped in things, that gravity can be trapped.
Particles come from all the stars in the universe. It's coming externally towards all these particles that are grouped together, and they're going to hold the nucleus together, they're going to hold the atom together, and if there's nothing in this space where these particles are passing, then nothing is happening. But if there's an atom there, it's holding it together. It's external.
So again, we already know it doesn't have the energy for that. So you have to add to that explanation, because that's just not enough.
So when the particle model has to explain to you, you cannot release binding energy because it's not there. There is no binding energy.
So that's pretty, it's almost a denial of, what we all can sort of understand, that's clearly releasing something. Whether you call it binding energy or something, it's releasing something, and it's something significant. It's not, well, I'll let him.
In the nucleus or the atom. So this is the particle model's explanation. It's all about conservation of particles first and momentum second. Particles balance. The number of particles here equals the number of particles here. There is no binding energy stored in the atom, therefore there can be no energy released, and therefore it's not heating the water.
All right, so the simplest argument would be if you just take this diagram and just think about it like it was a bowling ball and you're hitting bowling pins. Like, the pins can look like they're doing a lot of stuff, but they're only doing what the bowling ball provides. So it's energy in, energy out. So if you add up all the movement of the pins, it would add up to the momentum of the bowling ball. And so there's no extra energy anywhere, so you're not gaining anything. So why wouldn't you just make a bomb without splitting any atoms and just shoot neutrons? So it just doesn't make any sense. You can't get more energy out unless you're releasing more energy from something. And there's no explanation for why you would think the two byproduct atoms have more momentum than the original atom. And so unless you have some way of explaining how the neutrons, the three neutrons that are released, have more energy than the bowling ball that went in, this just doesn't add up to anything. Clearly there's some other kind of energy released.
What heats the water? The moving objects heat the water. The objects are moving. This is where momentum comes in. What is the velocity of this neutron? Presumably this has no relative velocity. After it splits, these are all moving.
Right, but the whole point of the chain reaction is created by compressing the material, therefore allowing the natural process to cause the chain reaction, so the neutrons don't have to be really injected. So they're coming out at the regular speed that they come out of the reaction. And so, even that you can't account for. How does one neutron going in create the speed of the three other neutrons that are equal to the energy that went in? So it has to be some sort of, extra energy. It just, has to be. Anyway, so the point here, that just makes this related is it's energy in, energy out kind of equations, and it relates in some sense, in some vague way, to the subject that I was thinking of, which is the electromagnetic effect. And it's the same thing, that you have these misunderstandings about these different experiments and which ones are talking about mass, or when they're talking about weight, or when they're talking about some specific thing, and it really does make a difference which one they're talking about. And so it can get quite confusing. So the Einsteinian photoelectric effect is a very different thing than the electromagnetic effect, or you could say. I mean, it's still a photo effect, right? I mean, we know that radio waves excite the electrons in a piece of metal and cause a current. And we have every reason to believe that any kind of radiation will do the same thing. So it's sort of a an effect, photoelectric effect, but it's not the photoelectric effect the photoelectric effect is talking about. So I'll try to make a clarification of these different things and explain what I need to, I suppose, in terms of adding whatever I would say this is what's happening kind of thing. I mean, I don't want to do too much of that, but all right, so the photoelectric effect really has to do with the, I probably should have drawn it in different colors because then I could use blue light as blue, but we'll use blue light as green. So green photons hit, that's blue light, and what happens is an electron actually leaves the material. So an electron is ejected. It actually shoots away, which is quite different than the idea of just creating a current or an electrical potential across the thing. It's an actual decomposition of the material. So this is creating ions. All right, so, and the other stuff you don't say is ionizing anything necessarily. So say when you're moving a magnet into a coil or into a piece of copper, you're not thinking you're making ions. You're just changing the electrical potential of the atoms. So it's a different kind of effect. So the argument is that red light, you could pump red light in all day long and you just won't ever knock one of these electrons out, so no matter how much volume you have. So I've sort of explained that I would argue that the atom is under tension, and in the sense that the electrons have a position and they have between them essentially a spring of energy. Those are little photons moving back and forth, reflecting. Now the momentum is absorbed and readmitted, but it's essentially a reflection. And so it's like a little spring. So anything that happens to one electron sort of happens to the others, and they fight back, so to speak. So the idea would be is that what happens in the photoelectric effect when you're ejecting an electron is that you have to somehow compress these springs enough where when they fight back, they shoot back with enough momentum to overcome the attractive force between the proton and the electron and allow the electron to escape velocity, essentially, acquire that. So the idea would be is if you understand, even just for illustration purposes, it fits their model and it also fits mine to understand the quanta, at least in this way, that a photon of blue light has its quanta at a tighter frequency. So whatever you want to think of the quanta as, whether you want to think of it as a wavelength, you want to do this crud, and think of it as this lumpy stuff. It really doesn't matter, because you're basically saying this is a quanta, or this is a quanta, or this is a quanta. So the quanta of the light is made more intense. Obviously I drew this very poorly because yeah, we're going to fix that. I just kind of ruined my own illustration by not drawing it right. I mean, obviously the red light has a longer frequency, so it has less potential, less quanta per square inch or per hertz or per, not hertz, but per unit of time. You can cram more stuff in blue light than you can red light. So the simple argument would be is that you can, if you hit the electron with red light, the red light hits in, moves the electron, compresses these springs, but the problem is because of the big frequency between when the things hit, this rebounds before the next one shows up. So it starts to be moving back this way from the spring pressure, so it's moving into, its momentum is against the particle hitting it, and so you're not going to compress these springs with that. You're just going to nullify those forces. But the blue light has the advantage, the circumstance, that it's essentially on the resonant frequency of the electron. So when the blue light comes in, it pushes the electron deeper with each impact. So it compresses these springs more and more. And then when you get the rebound, you have the momentum of the stored energy. So you stored a couple of arrows this way, and so now when that pressure stops and the other electrons fight back to go back to their normal pressure, they'll push in the opposite direction with the same momentum. So you've basically taken 3 pulses of ultraviolet light and turned it into one pulse, one big pulse of energy in a direction, momentum. So now you have enough momentum to escape the attraction to the proton, so the electron leaves. So that's why the high frequency light works, is because it can push more energy in, because it's past, resonant kind of implies that there's only one frequency and everything on one side is dead and everything on the other side is dead. But in a sense, when you think of it a pushing spring, it just means anything over a certain closeness will be faster than the rebound speed. So any energy faster than the rebound speed of the electron will be able to be stored and released. So it's not technically a resonant frequency, it's a storage frequency, but it has a lot of the same, it's similar in a lot of ways, so it is suitable as a description, I think. All right, so we'll just get rid of some of this so we have more board to work with. All right, so I think that explains the so that's the photoelectric effect. And it's confusing because obviously you have this other effect where photons, radio waves, can hit a surface and they'll create an electrical potential. So, a radio wave hits it and creates essentially a plus and a minus effect on the conductor itself that you can measure. So the conductor becomes polarized by a voltage based on the energy that comes in. And one would assume that this holds for all energy. So it doesn't matter what I really hit it with, I'm going to get some effect. So even infrared or heat will create some effect. And you can magnify that effect with a thermocouple. When you combine 2 metals and stick them together, you'll increase how sensitive they are to infrared radiation, and they'll create even more of an electrical effect. But that has to go, you get into chemistry with that one actually, so no point in getting into that too much. Well, it's not so much chemistry as it is the, what's the word for the electrolytic effect? So anyway, I mean it's chemistry, but it's, it can be dry chemistry actually. So anyway, so the thing that the other questions though is this other way. So this is essentially a photoelectric effect where you're creating an electrical potential. So you're obviously in some way affecting electrons, but it's not the photoelectric effect that was Einstein's photo. It's not this. It's not creating ions necessarily to create this voltage potential. I would argue all it needs to create the voltage potential is to compress an atom. So I've sort of explained before that I would argue that atoms can be pressurized. That is, they can absorb energy. And so we're using green for the electrons, I guess. And the energy will be stored between the electrons. And so the electrons can be at different sizes. And these different sizes have different electrical potentials. So if you inject energy between the electrons, going back to this example, the springs. So if you load the springs with more energy, that means everything gets pushed out because the electrons are pushing away from each other more, so they're moving further away from the proton. And in doing that, they now become electrically changed or biased, or whatever the word you want to use. So I would argue that when you push them out, you make essentially a positive ion, but you haven't changed the number of electrons, and it'd be negative when it's really small. And the neutral would be where the two forces are equal. And so what this really means is that the force that will radiate from these objects is going to be changed. I guess I can draw it on here. So here that would be, the force would be 50-50. So if you have these two force elements, the electron force and you have the same number of orange to blue, and that'd be a neutral atom. And when you change these sizes, I would argue that it probably just happens on one face of the atom, but it doesn't really matter. But when you change these distances, then you change the proportion from 50-50 to, say, 70-30 or something like that. And this would be 30-70. You don't need to make it too clear. I suppose you can get some of that on your own. And so the atoms are being, they have every appearance of being an ion, but they're not an ion. You didn't extract an electron and create a deficient atom, one short of an electron, which would mean it would be proton heavy. All you're doing is changing the distance between the proton and the electron, and by changing that distance, you're changing what it appears to be. It looks different depending on how far away the thing is. Changes how much of me you can see, sort of, that kind of effect. And that's what's creating the charged phenomenon in the atoms. So to get more specific on that point, let's just redraw it. I probably should use green for the surface and the other colors. Well, anyway, it doesn't matter. All right, so here we have our surface. Now we have two phenomenons that happen when you affect it. So this is a piece of aluminum, and that it's got no connection to ground. So there's no ground. So it's insulated. And you can affect it a couple of ways. You can hit it with this radiation directly, radio waves, and that'll create an electrical potential. Or you can expose it to charge. So I could take a charged object and bring it in proximity. So this, say, is negatively charged. And what's going to happen on that surface, at least in the cases we've seen, like, say, a charged ball or metal ball or something, is that this is going to charge opposite on this surface, and you won't get an electrical potential going through the conductor. You'll just end up with an electrical potential on either side of the conductor, which is, this other side will go negative. So essentially a charge, a monopole of charge, will create an opposite charge on the surface, which means you'll create attraction. The two things will attract each other. And your electrical potential will be across these two surfaces. Now the other thing you can do is expose it to use this one, a magnet. And so I can just put a magnet on the surface, towards the surface, move it. So the key thing would be is this charge doesn't have to be moving to create this effect. It just has to be getting closer at any speed, and it creates this effect. Now I haven't seen them take monopole charges and move them quickly into aluminum. So I can't say for sure what happens when you start moving a charge quickly into another charge. But, it is an open question. It's something I haven't figured out the answer to, so that's why I'm bringing it up. So in this case, when I'm moving a magnet into a paramagnetic material like aluminum or copper, is that I get the same charge created on at least this portion of the surface at any rate, and I end up with so I end up getting a repulsive charge here. The two things end up repelling, and I end up with an electrical potential that isn't going from side to side, but is going from plus to minus. Let's just put a fake line here. So I end up creating an electric current this way in the conductor. So instead of this current from side to side, you create a polarized current from end to end when you use a magnet. Now, theoretically, in my opinion, these two things are the same thing, just manifest differently because this is a dual. Like this is, a magnet is got both bits of reflective energy, and it's a dipole, and that has a consequence. Where this is a monopole, this is magnetized throughout the whole material, creating a lot of filtering, where this is only charged on the surface, so it has little ability to filter the world, but it has a great deal of ability to reflect what comes at it. And let's see what else. So this charge doesn't dilute over distance. So this does the r squared thing, where this does the r cubed thing in terms of getting weaker at a distance. So this one works well close. This one works well far. And you have this opposite effect. I should have used the magnet switch the other way so you could see the oppositeness, obviously. But yeah, so in one case it creates the same, it gives back what you impose. So that could be understood as the atom being, I have to get that in, go down here. So if you understand, the force comes in and basically pushes the electrons flat, and the proton doesn't have time yet to move, so the atom becomes polarized, and so it becomes, in this case, in the case of the charge, it ends up giving you back the opposite, where in the case of the magnet, it ends up giving you the same. And there's some reason there's a difference, and the difference has to do with which way this current is going. You can sort of see. So in some sense, you can figure out maybe that the dipole causes this material to change in this direction. Length to width, and this one causes changes in the opposite direction. But I haven't figured out exactly what those would be. Well, anyway, so that's probably enough just to open the door to, like I said, it all fits. And then you'll find one little circumstance that doesn't fit the rest of the circumstances, and those are the ones that have to be explained. I don't know if there's a point in getting into the, I guess I can erase this bit because you've seen this long enough now. I have to become a more efficient eraser. Left us a little bit of a mess there. That's okay. The other thing I've pointed out is we know when you use a magnet that the conductor ends up charging in a particular right-handed rule kind of way, so that the whatever magnetism is being created has an obvious bias in its polarity. That is, it always lines up this way, so that all the magnets have the same character. They all go from orange to green, and they go all the way around orange to green, orange to green, and so that you end up having the face that you see. You'll have a plus end and a minus end around the circumference of the wire. So the polarization of the wire is in this direction across its circumference, not down its length. And obviously in these other circumstances where you're not creating a current, but you're creating a charge on these two surfaces, the effect is being seen lengthwise of the conductor rather than across the conductor. And so that's the circumstance that I don't yet have a complete answer to why there is that difference, just as I don't have a complete answer as to why there is a right-hand rule, why it picks right versus left. The fact that it would pick a side seems intuitively reasonable, but why does it always pick the same? Why does it always go that way? Yeah, so I don't know if I have to. It's the so it gets very there's a lot of stuff to this, and it's unfortunately when they when somebody presents these things, they present them in little packets, separate effects, and they're all doing very similar things. So it's like, the experiment should be done at the same time, in a sense, to illustrate, well, this is what a charge thing does, this is what a magnet does, this is what, if I move it, what happens, if I move it, what happens. There's just not enough of that in these experiments to demonstrate these curious circumstance that if I move a charge into this material, I'll end up with an attractive force, and when I move a magnet in, I end up with a repulsive force with paramagnetic material. And sort of that asks for an explanation. Yeah. So anyway, yeah, so that's probably enough for this edition. So I'm working on it and all that kind of crap. Gotta get rid of this glare light, I guess. It's coming from that light behind me, I guess. Well, some of it is. Some of it's coming from above me. Okay. Can't really do much about that, I don't think. I mean, I could put a... Oh, it's coming from way over here. That's weird. I mean, maybe if I put something over the microphone. That gets rid of some of it. Well, anyway. There's too many things to worry about here. Too many. I move my screen, I suppose, but that doesn't do much. And I don't really want to turn the overhead lights off because they're sort of necessary. Anyway, yeah, I'll work on it. Lighting, it's always a problem. So till the next time, probably, and such, so forth and whatnot.